Hi guys, welcome to Science Chomp. Today we're going to be talking about half-life. Now I've actually discussed this at great length in my previous video, but that video was a little bit long, so I want to do one which is more science chompy, something a little bit shorter. So just only half-life today. So again, I would strongly recommend you watch the previous video, but if you don't want to sit through 20 minutes, just sit through this. Okay, first of all, half-life depends on radioactive decay, which is when an isotope, which is a form of an atom, decays to form a different isotope. So you have the parent isotope decaying into a daughter isotope. In this case, we have a neutron, and what happens is it decays to form a proton. When it does this, the actual identity of the isotope changes. So here, because we've got one proton, it's hydrogen. Here we've got two protons, it's helium. Okay, so if you want to know how we name these, basically you just count the number of protons, look at the periodic table. Anyway, what happens is this basically. So here we've got some nuclei, radioactive nuclei, and they're undecayed. So this you would say is, I don't know, isotope A. And when it starts to decay, can you see it all turning blue? The amount of red, amount of isotope A is decreasing. It never actually hits zero, because no matter how many times you divide a number by 2, you're never ever going to get to 0. So that's what's happening. This is like the half-life curve. And to determine the half-life, what you do is you go to 50%. So that's the 50% of nuclei that have decayed. You go across, so you start at 50, you go across, and then you go down. And here it seems to be around 20 seconds, okay? Now, to give a quick definition of half-life, it's this part here. So an isotope's half-life is the time required for half of the parent's isotopes to decay into daughter isotopes. Okay. Now, when you get into absolute age dating, if you've got an organic piece of material like a dead plant or a dead animal, you use half-life of carbon-14. Okay. So what happens is the carbon-14 has a half-life of 5,730 years, meaning that if you've got like a sample of carbon-14 in 5,730 years, you're going to have half the amount left. So say, for example, you started off with 10 grams of carbon-14 in a particular sample. After 5,730 years, you will be left with 5 grams, literally half the amount. Okay, so half the amount, and you go down 5,730 years. So if something's organic, you can use carbon-14 to figure out how old it is. Basically, you see how much you've got left as a percentage. You go across, you go down, it tells you how many years have gone by. For rocks, this isn't going to be good enough because the half-life is too short. So we use other radioactive isotopes, for example, these ones here. So these have a much longer half-life, and for a really old rock, you want something with a much longer half-life. Here you can see the half-life curve of uranium-235, which is one of the isotopes that they use to date rocks. And as it decays, it turns into lead, which you can see here. So as this gets smaller, the lead gets bigger. At the 50% point, so this is the half-life, if you go down, you can see the half-life of uranium-235 is around 700 million years. Okay, well, that's it for half-life. Thank you very much for watching, and goodbye.